Okay, guess I'm audible. Yep. So, yeah, welcome to week 11 live session of digital signal processing. I am Sai Dinesh Kancharana. I am the PMRF, NPTL for this course. So, this week I'll be covering topics about sampling, right? And I'll be covering some material from what has been taught in the class, and then I'll be discussing about some hints of the assignment questions, right? So, yeah, week 11 live session. So first, so in this week we are mainly talking about sampling. Okay. Um. Yeah. So basically, so we'll be working. Uh. So we'll be working with computers, is it? So then we need a digital form of a signal. So right. So digital meaning it's a subset of being discrete, right? Digital is either 0 and 1s. We'll be mainly working with discrete signals. 1 second, sorry. Yeah. So we'll be working with discrete signals, but all real life examples, real life signals are actually continuous. So, but we will be working with computers which is in discrete form, and then once we got the signal in discrete form, we process that in discrete form. So that is what is the discrete digital signal processing, right? So if you see it as a block diagram, a continuous time signal xc of t. Okay. So x of n is equal to xc of nt. So this xc of t is actually the continuous time signal, right? And this is a discrete time signal. This is actually the sampling time period. So basically what we do is we take equally spaced points from the continuous time signal, right, and then convert it into a sequence to get the discrete time signal. Okay. So we refer to the system that implements this operation as or the continuous to discrete time converter. So we have x of n is equal to xc of nt. So the system the top that does this operation is continuous to discrete time converter, right? Now how do we do this? So let's say we have a continuous time signal, so we want to take periodic samples of that signal, right? So how do we do that? We do that using a impulse train. So what is an impulse train? It is a train of a periodic impulse, a periodic signal with equally spaced impulses, right? So impulse train. So this is actually an impulse train, when weighted impulse train. Impulse train is basically like impulse signals at equally spaced intervals. So this is xc of t, excess of xc of t, and the ones if you multiply it we get excess of t. So this s of t is known as the impulse train, right? Minus infinity to infinity delta of t minus nt, right? So delta of t, delta is the impulse function, and if you see, this is a periodic repetition with sampling period t, right? So at every t interval there is a impulse. So if you multiply this impulse signal with, if you multiply this impulse signal with this continuous time, we get equally placed samples of the continuous time signal, right? So xs of t is equal to xc of t into s of t, which is equal to xc of t and equal to minus infinity to infinity delta of t minus nt, which is equal to minus infinity to infinity xc of t into delta of minus nt. But according to the shifting property, we know that x of t into delta of t minus t naught is equal to x of t naught into delta of t minus t naught, right? So if we apply this here, this implies the new sampled signal xs of t is actually equal to x of nt xc of del t into delta of t minus nt, right? So the size of the impulse at the sample time nt is equal to the value of the continuous time signal at that time, right? So this is actually again a weighted, this seems like a weighted impulse train, with weights being the values of the continuous time signal at that particular time instance, right? Now what do we have? So after we get this, so now it's like we have a continuous time signal, we multiply it with an impulse train, we get a, what we get is an impulse train, right? So this is what we get. So this is xc of t times t, and what are the time instance? These are t, 2t, 3t, and so on. So this is the excess of t basically, right? So now one thing is this periodic sampling of, so I have mentioned it here, 2t, 3t, etc., right? So this periodic sampling can be done at arbitrary time time period, right? So this can be t1 and this can be some week. Again we can sample the this at a very different. So this is t1 and let's say this is t2. For t2 is greater than t1, that is like low sampling frequency, right? This is a lower sampling frequency. Okay, so what we can understand from here is that, so now what do we get? It's only 4 samples, right? This is what we get: t 2t, 3t, and 4t. So if we see that, if we do the sampling at adequate amount of points, then we can recover the original signal. Here we can actually like recover the original signal like this, but here this can be like this, this can be like this, anyway, right? But if the samples are close enough, we do not have. So basically this, what we should ensure is that the in the difference between these two between two samples, there should not be too much deviation, right? So if the distance is more, it can have very high deviations, but if this distance is very less, it's not possible, right? So the frequency at which the signal changes determines the frequency at which we should sample the signal. So this is the basic intuition, right? So if we know that the signal has very high frequency like this, then we should sample it even more, right? So intuition. So we can clearly see this intuition in the discrete time domain when we in the frequency domain when we take the Fourier transform of this signal. Okay, so we moved the frequency domain representation of sampling, right? So, and okay, I forgot to do one thing. So this actually is still a continuous time signal. So we need to still bring the continuous time signal to a discrete form. Now how do we do that? So we actually generate a sequence, actually generate a sequence which has so this is x of n. These are the values: x of 1, x of 2, x of 3, x of 4, where each x of n, the value at the discrete time signal is equal to the value at the sampled point of the continuous time signal. Right? So here we are so here the axis is t, 2t, 3t and 4t. Now here we bring it to 1, 2, 3, 4, right? So we are time normalizing right? And also in this, as we have discussed throughout the course, it does not exist. Here it is equal to 0, right? Equal to 0. Exist. So this is how we move from discrete time to a discrete time signal. So first, continuous time signal to a discrete time signal. First we have a continuous time signal, we multiply that with a impulse train, and then we get a weighted impulse train where the values of the impulse train, the samples, are equal to the values of the continuous time signal sampled at that particular time instances, and then we move that continuous time signal to a discrete form, right? So this is, so finally this, now this is the, sorry, this is the discrete time signal. Okay, now if you see the frequency domain representation, now we move to the frequency domain representation, right? So this, you see, s of t is actually equal to the impulse train, right? So t n minus t, sorry, let's take it as okay, t, right, n equal to minus infinity to infinity. Now the taking the in frequency domain, we have this equal to 2 pi by t into omega minus omega f, where this omega s is equal to 2 pi by t is the sampling frequency, right? So this omega s here, capital omega s, is the sampling frequency at where t is a sampling time, right? So this actually defines, so if we have very high value of omega s, this means we are sampling more rapidly, but if we have low, so this means omega 2 is less than omega 1. Okay. Omega, so this is, so an impulse train in the time domain is actually again an impulse train in the frequency domain also, right? Now one more thing that we knew earlier is this xs of t is equal to xc of t into s of t, meaning in the frequency domain, I'm saying CTFT because these are still continuous time signals, right? So in the continuous time frequency response of xs of gem xs is equal to 1 by 2 pi xc of j omega convolved with s j omega. Okay, now what is this equal to? 1 by 2 pi xc of j omega convolved with 2 pi by t minus infinity to infinity omega minus k omega s. Okay, so again we know that convolution using the concepts we have discussed earlier, the convolution with an impulse signal is simply the time shifted version of that signal, right? So finally what do we get is this 2 pi and this 2 pi gets cancelled, and what we are left with is one by t times k equal to minus infinity to infinity xc of j to k omega s. Yeah, so basically this is the periodically shifted periodically shifted. That is first one, and second one is gain equal to 1 by t, right? So no, so this is the relationship between the Fourier transforms of the input and output of the impulse train modulator. So right now this states that the Fourier transform of x of s, which is this, consists of periodically repeated copies of xc of j omega, which is the Fourier transform of xc of j omega. So xc of t, which is the Fourier transform of xc of j omega, right? So these copies are again shifted by the integer multiples of the sampling frequency, right? So if we have a frequency domain representation, this is periodically shifted by omega s. So the center frequency of this is 0, this is omega s, this is 2 omega s, and so on. So I'll write formally. Okay, no, right, so let's take an example, right? So let's say vectorial representation in frequency domain, right? So let's say we have omega n, which is xc of j omega, which is this is the continuous time Fourier transform of xc of t, which means it is not periodic in 2 pi unit when. So we know that dt of t is periodic in 2 pi and ct of t is not periodic in 2 pi. Okay, I mean maybe, but here it is not periodic, right? And then we have the impulse train, okay, which is, okay, I'll write a little bit farther. Okay, now this is 2 omega s, which is equal to 2 pi by t omega s. This is equal to 2 pi by t. So this omega s, which is equal to 2 pi by t, this is 2 omega s, this is minus omega s and minus 2 omega s, right? So this actually is the CTFT of impulse train with time period equal to t, right? So frequency is 2 pi by t and it is periodic. So we have impulses at omega s, 2 omega s, where omega is equal to 2 pi by t, right? So if we multiply these two, we have seen that what we get is a shifted version of the original signal with the gain of 1 by t, right? Okay, so this is 0, this is omega s, this is omega n, this is omega s minus omega n, this is minus omega n. So this actually is excess of j omega, which is still a CTFT, right? Still a CTFT, since it is still continuous. We have not gone to the digital domain yet. CTFT of excess of t, which is equal to xc of t into s of t, which is multiplied. So signal which is multiplied by the impulse train modulator, right? So excess. So if we here we see that if omega s is greater than omega s minus omega n, sorry, one second, is it right? So this is omega n, right? So this is omega n, this is omega s minus omega n, which means omega n is less than omega s minus omega n, which implies omega s is greater than 2 omega n. Then there is no aliasing, that is no information is lost, right? But if omega is less than 2 omega n, then there is aliasing, that is high frequency content is lost. This is the so what does this mean? As I've told earlier, this is the sampling frequency, this is the twice the maximum frequency of the original signal. So this sampling yes, exactly. So sampling frequency, the sampling frequency should be greater than twice the maximum frequency of the original signal. So this is what we have seen earlier. So if this is the maximum frequency, then the sampling so if this is the maximum frequency, then the sampling frequency should be twice the twice the maximum frequency. So in that way, the rapid changes of the original signal are captured with sampling, right? So if let's say this is the maximum frequency, and then we take the sampling frequency which is lesser than that, then we are missing out the rapid changes between the two samples, right? So in that case, the information is lost. That is what actually aliasing is. That is what aliasing is. Aliasing. Okay. Now what can be done after this is, I'll copy this. Okay, so this, in this case, now we can, so actually one more thing is that there is a gain of 1 by t here. So if we take an ideal low pass filter, and we band limit to the center frequency around to the band pass region, then we can recover the original signal, right? Clear? So yeah. So let's say this is omega c cutoff of the LPF filter, and assuming there is no aliasing, that is omega s is greater than 2 omega n, then if omega n is less than or equal to omega c less than or equal to omega s minus omega n, right? So this corresponds to here, this corresponds here, right? So omega c should be in between them, right? So it's like omega s minus omega n and omega n. So this is omega c, the cutoff frequency. So if this happens, then xr of j omega, which is again xs of j omega times hr of j omega, is equal to xc of j omega, i.e. perfect reconstruction. Clear? So this is the conditions for perfect reconstructions for the continuous time signals. Now until now we have only talked about the continuous time part, but we have still not gone to the discrete part, because but what we're eventually interested is the discrete time part, is it? So we need to move there. How do we move? As we have discussed earlier, the time normalizing concept, right? We have seen that x of n is equal to xc of nt, right? So let xc per j omega is the dtft of x of n, right? So what is the relation between xe per j omega and x of j omega? What is the relation? That is what we need to find. We have seen earlier, so if this is x of n, then according to DTFT formula, x e per j omega is equal to x of n e power minus j omega n. But we have also seen that xs of j omega is equal to what? xc of nt e power j omega d n, right? Which is the CTFT of xs of t, right? But we know that these two are equal, right? So this is overall n minus infinity to infinity. Again, this is also overall n minus infinity to infinity. So now this is actually overall n x of n e power j omega t n xs of j omega, right? So let's say this is star and this is hash. Now comparing star and hash, we can say that ss of j omega is equal to x e power j omega at omega is equal to capital omega times t, which is equal to x e power j omega t. Right, so if we apply, if we change this omega is equal to omega t, omega t, what we are left with is this formula becomes here, right? So finally what do we know is, so this is the basic stuff, so this is the important stuff. So if we take the omega, if we take the capital omega and normalize with, that is multiply with t or divide by 1 by, or multiply with t or divide with f, what we go to the discrete frequency omega, right? So what corresponds, so t in yeah, so 1 by t in omega, 1 by t or fs or 1 by ts in omega equal to 1 in small omega. So this is eventually that time normalizing thing. So and then again, while finally comparing, what do we get is x e power j omega t, which is this one, is equal to, what is xs? We have already seen that it is a time shifted version, right? So 1 by t k times k equal to minus infinity to infinity xc of j into omega minus omega s. I will write it neatly, j omega minus k omega s, right? Or equivalently e power j omega equal to 1 by t, omega is what? Omega by t, right? So xc of j into omega by t minus 2 pi k by t, k equal to minus infinity to infinity. So this is the final form, that is this is the final relation between xc power j omega and xc of j omega, or x of n and xc of t. That is the discrete time version of the original signal, right? So as you have seen, if we go to the previous, if we continue from the previous case, right? So with a change in a small notation, right? So let's say this is omega c, this is omega s, right? And this is 0, and then what is this? xs of j omega. How do we move to the discrete domain? Which is omega s into t. Everything gets time normalized, right? So omega c into t, etc., right? But what is this? 2 pi by t into t, which is equal to 2 pi. So basically what we have here is, so what we have here is a 2 pi periodic dtft of x of n, right? And then we have 1 by t here. Clear? So this is the concept of sampling. right? So I'll go to the assignment questions for a bit, and then later we can. Yeah, okay. So first I'll go to the assignment questions. Okay. So not sure if this is opening. Okay, I have it open in my PC. Um, so I'm not able to show. Maybe I can like, write down the question or something. Wait, 1 second, guys. My iPad is getting really hot. I hope I'm audible now. Hello, hello, hello. Okay. So assignment assignment 11, question 1 says that if t is the sampling period, t is the sampling period, the relation between analog frequency the relation between analog okay analog frequency f naught and digital frequency small f naught is f naught equal to capital F naught times t. So I have actually discussed this question just a while ago. So this is the relation that we have just discussed. So this is discussed above, right? And then question 2 is, suppose the bandwidth of a given continuous time low pass signal is fc. Pass signal has bandwidth fc. The condition of the sampling rate fs for exact recovery. This is also again condition on sampling rate fs for exact recovery. So this is what I have actually discussed just a while ago again. So 0 fs fc fs minus fc, right? What is the condition for no aliasing? Next, question 3. Let x of n is equal to 2 cos omega naught n, where omega naught belongs to 0 and pi. So based on this information alone, can we deduce the true frequency omega or not corresponding to the continuous time frequency, continuous time signal x of. Okay, so this is omega naught, and this says xc of t is equal to 2 cos omega naught t. So this omega naught to this omega naught is it unique? So we have seen that this omega naught is actually omega naught times t, which is the sampling time period, right? So based on this, I guess you have got the answer. Question 4 is, for a low pass signal, for low pass signals, as the sampling frequency increases, the magnitude of dtft at omega 0 increases. Is it true? So we have seen that from omega c at xc of t, we have gone to omega c times t, but here we have a gain of 1 by t, right? So based on this, again I think we can get the solution. Next is question 5. It says a low pass signal xc of t that is band limited to fc hertz is sampled at fs greater than 2fc hertz, right? So yt is the reconstructed signal, right? So it is the reconstructed signal, and this is the Nyquist. So here we know that this is a it follows the Nyquist theorem, meaning the frequency at which it is sampled is greater than twice the maximum frequency of the original signal, so it can be actually exactly recovered. So yt is the reconstructed signal, assuming that the sampling sorry sampling and reconstruction process are ideal, max of x of t minus y of t decreases. Is it true? So you know that if fc greater than 2fs, exact reconstruction is possible. So if we take any other fs dash which is greater than fs, still the exact reconstruction is possible. So the difference between the original signal and the reconstructed signal, what does that happen? No. Next question is question 6. Let x of t be a low pass filter. Okay, let x of t be a low pass signal. I copied it wrong. So if t be a low pass signal, that is band limited to fc hertz, where fc is greater than 0.5 hertz. So and its corresponding impulse train sample signal is xs of t. Same notation. Let xs of omega, okay, xs of t has a continuous time Fourier transform of xs of omega, and the digital signal of x of n has dtft x e power j omega, where omega is actually 2 pi by t. So what does this happen? So we have seen that We have seen that. What have we seen? X e power j omega is actually, so SS of omega is x e power j omega at omega equal to omega t, which is x e power j omega t. So this is the so this is what happens in the frequency domain. So mark the corresponding solution appropriately. Okay, and question 7 is, let x of t is equal to cos omega naught t, where omega naught is 10 by 3, right? 10 pi by 3. Therefore 2 pi f naught is capital F naught, that is 10 pi by 3 implies f naught is 10 by 3, which is 3.3 hertz. Okay, now it is sampled at fs is equal to 3 hertz. So is fs greater than 2f naught? No. So 2f naught is 6.6 hertz. So what does this sampling? It is undersampled. Clear? Next, question 8. Question 8 states that, so let x of n, second, so let x of n is xc of nt be the discrete time signal obtained after sampling the original analog signal. Xc of t is 2 cos 2000 pi t plus sine 5000 pi t at a sampling frequency at 5 kilohertz, right? So dtft, so what is dtft? So this is the question. So if we have let's some like, right, xc of t is equal to cos omega naught t. So in that case the dtft, sorry, the ctft will be pi times delta of omega minus omega naught plus, so this is capital omega minus omega naught plus delta of omega plus omega naught. Now after sampling, what will it be? Excess of t, yes, you've seen this earlier, which is a shifted periodically repeated version of the original x. So this is xcf omega, right? Now xs of omega is equal to 1 by t of k from minus infinity to infinity pi of omega minus omega naught minus k omega s. Okay, I'll write it a little bit neatly. Minus infinity to infinity pi times omega minus omega naught k omega s plus delta omega plus omega naught minus k omega s. Yet, but we know delta of at plus b is equal to 1 by mod a delta of t plus b by a. So applying this here, what will we get? 1 by t times fs delta of okay before doing that, if we go to the discrete time domain, xe per j omega is equal to xs of j omega at omega is omega times fs. Sorry, no, it is actually omega is equal to omega times fs. True. Omega times t, which means omega is equal to omega times ts times fs. So this equal to 1 by t okay, I'll remove this, copy, sorry, okay. So k equal to minus infinity to infinity delta of omega fs minus omega naught minus k omega fs omega s delta s omega fs plus omega naught minus k omega s. What we know? So if we apply this, we have 1 by t s into fs into sigma delta of omega by fs plus by fs, right? But this is 2 pi fs and these two get cancelled, so this is actually equal to 2 pi and these two get cancelled, and what we are left with is finally k equal to minus infinity to infinity delta of omega naught by fs minus 2 pi k plus delta of omega minus omega plus omega naught by fs minus 2 pi k. So apply this in the formula. Apply this concept in the problem. Okay. Question 9 is, which of the following signals have Nyquist rate same as x of t? One is x square of t, x of 2t, del xt by del t. Fourth one, minus infinity to infinity, x of t minus tau, x of tau dt. Solution: take x of t is equal to cos omega naught t as example and verify. 1 and 2 not possible. Now 10th question. Question number 10. X of n is cos n pi by 4 x of t cos omega naught t. Fs is 1 kilohertz, which is cos 2 pi f naught t. Xc of nt is equal to x of n is equal to cos 2 pi f naught by fs times n, and this is equal to pi by 4n. So 11. One second. So 11th question is, x of t is equal to cos 2 pi f naught t, where f naught is 200 hertz and fs is the sampling frequency is 280 hertz, right? So x of n is cos 2 pi f naught by fsn, which is cos 10 pi by 7n, and if you 200 and 280 gives you 10 pi by n. Now we know x of n, sorry, y of n is x of n convolve with h of n, and h of n is 2 for n equal to minus 1, minus 2 for n equal to n equal to 1, and 0. Oh, 1 second. Is this correct? Yeah, and 0 otherwise. So this is actually equal to delta 2 times delta n plus 1 plus 2 times delta n minus 1, right? So delta of n convolved with x of n gives x of n. Similarly, y of n is what? X of n convolved with 2 times delta of n plus 1 plus 2 times delta of n minus 1, which is 2 times x of n plus 1 plus 2 times x of n minus 1. Clear? 12th question, x of t is k minus 5 to 5 j k e power j 15 pi kt. So k equal to 0, 1, 2, minus 5 to 5. So max frequency is 15 pi into 5 into t, which is 75 pi t, right? And then they occur in pairs in the summation, i.e. j 5 into e power j 75 pi t plus e power minus j 75 pi t. So which is actually sine of 75 pi t. It's a maximum frequency. So this is maximum frequency. What is fs? This is what needs to be found out, right? So in this class we have discussed about the concepts of sampling, and then we have discussed some assignment questions. Please let me know if you have any doubts in the discussion forum. Thank you.